Hello, everyone. So we're going to start. Thank you for being here and members. I don't know if you have noticed, but lastly, we had some problem with the seminar to find people to present. So don't hesitate to contact us, Eneko, Chiska, Sofia, or me if you want to present one day. Today we have Diego from OFC Group, and he will present part of his work, and I let you in Diego.
Okay, so thank you very much, Paul. Well, hello everyone, and thank you very much for coming today. So today I want to talk to you about the ocean and how the ocean moves and how we can capture this movement and the transport of physical and biochemical properties in the ocean, in particular in the Mediterranean Sea, and the different approaches that we can follow to track this transport. Here, a little spoiler. So we want to use, or we are going to use, a Lagrangian approach to track vortices in the Mediterranean Sea across 30 years of altimetry data. But yeah, what the heck means Lagrangian? So let's start with a little bit of history with two people, two scientists from the 18th century, Euler and Lagrange, and different perspectives that they use to track the properties in a fluid. In the Eulerian perspective, we have a fixed point in time, in space, or a volume of this fluid, and we can track how this fluid change within this space. And then we have the Lagrangian perspective, where we can follow, or we must follow this water parcel, this water mass, through time, and we observe how the properties of this water mass are changing. So yeah, equations. Math is scary sometimes. So let's have an example. You can imagine a river, and we want to track the properties in the river, and you have two options. We can sit in the riverside and focus on one single point in the river and check how the properties are evolving. So that would be the Eulerian perspective. But we can sit on a boat and follow the flow, the current of the river, and check a fixed point relative to us in the river, following how this point is transporting through time and how the properties are changing through time. That would be the Lagrangian perspective. These two perspectives are used in the platforms that we use to measure the ocean. Here you have a very nice illustration of all the measuring platforms that we have that we use in the ocean. The Credit for Marine Copernicus Marine System service have a bunch of different platforms. Some of them are remote platforms like satellites or HF radars. But also we have in situ platforms like buoys that can be fixed to the ocean bed, or also drifting moorings, gliders and sailing drones that they have their own motion. And also we have research vessels. But also we can divide these different platforms in Eulerian and Lagrangian platforms. In particular, the Argo profiled floats and the drifters, the drifting moorings, are Lagrangian platforms that drift across the ocean following the currents. However, the in situ platforms give us a very nice temporal resolution of the measurements, but a very scarce spatial resolution. Imagine that we have to we have to launch a lot of drifting moorings to have a nice spatial coverage. However, with satellites, we can have a very good spatial and temporal resolution. They're following their orbits. And it's true that they have less temporal resolution than the drifting or the in situ measurements, because they have to complete the orbit across the Earth to get another measurement. But the good thing about the satellite data is that we can reconstruct an almost continuous aggregate field of variables that will allow us to reconstruct virtual trajectories, and that will help us to develop these Lagrangian metrics and Lagrangian variables. So, as I said to you before, we're going to use this variable field from satellites to do simulations of particles. We talk about particles, but you can imagine like water parcels or small in situ drifting platforms. And we can simulate their trajectories. Here you have a little example of different particles initialized in the Mediterranean basin and how they evolve through time. The colors represent the distance between the initial position and the current position. You can easily see that some of the particles reach the coast. You can see these blank regions where we don't have any more particles. There are some others that drift very far away from their from their deploying positions in some kind of filaments or meanders across the Mediterranean Sea. But some others are retained in rotating structures that kept the particles through time. With Lagrangian approaches, with a Lagrangian approach, we can define different metrics to track the transport of these particles. One example is the finite size Lyapunov exponents. Okay, yeah, it's a very long name, but you can imagine that this Lyapunov exponent simply measures the time that takes two particles initially separated at distance delta zero to reach a separation of delta f. But what this indicate? Well, this exponent indicate? Well, simply it indicates the barriers to the transport of particles, the barriers to the transport across these filaments, but the transport along the filament. So you can see two clusters of particles. In the first one is trapped between an almost closed contour of Lyapunov exponents, trapping the particles within its interior. However, the blue one, it's not trapped by this exponents, and the particles travels along the different along these exponents. But this is a simulation done again with the same satellite-based data set. But this information also allow us to track real platforms like real drifters from the pre-SWOT campaign. You can see in red the different drifters and how they follow the paths that are defined by the Lyapunov exponents, giving us a lot of information on how the different properties in the ocean can be transported or trapped in the different structures. Also, as I said, these Lagrangian structures can be used to track or to trap biochemical properties like the chlorophyll. There are a lot of different works showing how Lagrangian structures can track and trap blooms of chlorophyll and track them through time, and how these structures, these Lagrangian structures, define better the barriers of the confining structures than the Eulerian perspective. For example, in this example from Johnson's Challenge in 2024, they define Lagrangian structures around a maximum of chlorophyll, and also they define a Eulerian structure and show how the Lagrangian structure have a higher maximum of chlorophyll than the Eulerian structure, showing that the maximum of chlorophyll it's much more confined by the Lagrangian structure than the Eulerian one. Also, in a paper from Ismail, he managed to identify a maximum of diatom bloom relative to a Lagrangian structure, and it's much better captured than in using an Eulerian approach. So yeah, that's the introduction. a very long introduction. So let's start with our work. So we want to recompute the rotational coherent Lagrangian vortices, or to short them Lagrangian vortices in the Mediterranean Sea. This work is already done at global scales, but we know that the Mediterranean Sea, it's a very special basin, semi-enclosed basin with a lot of coastal areas. And also we have the privilege to have a special satellite-based product focused on the Mediterranean Sea with special tuning from the Mediterranean dynamics. So to compute these Lagrangian vortices, we start, as I said, with the velocities. And then we can simulate the trajectories of the particles and we compute the Lagrangian vorticity. How we do this? Well, we have the trajectories, and then each step of the trajectory, we integrate the vorticity. The vorticity is simply a measure of the sign of rotation of the fluid. We track the particles backwards along a time, t, a Lagrangian coherent rate. It's going to be very, very important because the characteristics of the transport are going to change depending on this Lagrangian coherent rate. So after computing the Lagrangian vorticity, we obtain this kind of maps with some maximums of vorticity and clusters or vortices and some other filaments and yeah, a lot of different structures. And once we have this kind of maps, we identify the coherent structures. We have a bit of complex algorithm, but it's going to be explained very simply, that it's just simply the identification of relative maximum of Lagrangian vorticity. You can imagine that these structures have their own maximum, like a peak. You can imagine mountains and valleys of vorticity. So we identify the maximum and minimum points, and we draw an isovorticity contour surrounding these maximums. Why we do this? If you can imagine an idealized vortex, you have like a perfect cycle, and the particles are rotating along the cycle. However, at the end of the life, this perfect cycle is going to unravel into filaments. So when we start to having this filamentation, we're going to start having this kind of concaves. So we're searching for almost convex isovorticity contours around the maximum. These are going to consider as possible contours that maintain the particles within its interior throughout its life. But we want to track the particles that if they truly are kept inside the contour during this life. So we do this and we check the dispersion of these particles. And if they don't disperse very much, we say, okay, yeah, this contour maintains the material within its interior during its life. Then the last step is to track different Lagrangian vortices across time, the collocated Lagrangian vortices in the following days. So at the end of the algorithm, we have maps like this, where we identified contours that we can assure that the particles of the material within its interior are trapped during their lifetime. Because I said that the time that we use to integrate all these particles, it's very important to understand the different properties of the transport. We have a the sensitivity study on how the properties of these Lagrangian vortices changing the Lagrangian coherent rate, the time that we use to make the trajectory of the particles within the contours. Here you can see that there are a lot of variability depending on the Lagrangian coherent rate in light colors. In light colors, very short Lagrangian coherent rate, and in dark colors, very long coherent rate. Also, you can see that there's some variability in the anticyclonic eddies in blue and cyclonic ones in red. Also, we can see that there are identification of very long eddies and very well-known areas where we know that there are permanent eddies like the Alvaran Sea or Yera Petra, but some others that maybe are not well known. For example, this is just an example for 2023 and 2022. And we see that, for example, there are very stable cyclonic eddy in the Ibiza channel. That's very, very interesting. But we are interested in the variability between the different Lagrangian coherent rate times. See that we identified more Lagrangian eddies with a shorter Lagrangian coherent rate, and this number decreases with the Lagrangian coherent when the Lagrangian coherent rate increases with a power law. That this can be related with the turbulence in the ocean, but we have to further study it. Also, we are very interested in the polarity. Here you have the ratio between, the polarity is the sign of the vorticity. If you have an anticyclonic, that is a clockwise rotating eddy, or a cyclonic eddy, that is a counterclockwise rotating eddy. So we are very interested in what's the ratio between cyclonic and anticyclonic structures. We have computed this ratio in Eulerian eddies, and we find that it's almost 1, like 50% of anticyclonic eddies and 50% of cyclonic. When we use short Lagrangian coherent vortices, we obtain the same result, a very similar result. However, when we increase the Lagrangian coherent rate, the time that we integrate, we are losing cyclonic eddies, and almost all the cyclonic identified are anticyclonic. Sorry, all the vortices identified are anticyclonic. This is not new, because in an Eulerian perspective, we already can see that the Eulerian eddies are longer, are tracked for more time than the cyclonic ones, but we see here that the anticyclonic ones are more coherent, they track better the material with its interior. But what's happening with the particles within the interior, and how it's different, the Lagrangian approach from the Eulerian approach? So you have launched the particles inside the Lagrangian Eulerian vortices, and we let them evolve back in time, and we have checked the absolute dispersion, but it's simply the spatial variance of the cluster of particles at each time relative to the initial time. we have computed the median, and we obtain this plot where you can see the Eulerian, the particles started at the Eulerian vortices in black dashed lines, and in colors, the rest of the particles initialize in the Lagrangian vortices, depending the color on the different Lagrangian coherent rate. So the negative values of the absolute dispersion indicate growing in the cluster of the particles, more dispersion. Positive values or less negative values will indicate less dispersion. So we find that the Eulerian eddies have the most dispersive structures. They trap particles not very efficiently because they disperse very quickly in comparison with the Lagrangian vortices. However, we can see that when we increase the Lagrangian coherent rate, the colors, the blue colors or the purple colors indicate like 10, 20 days of Lagrangian coherent rate, and in yellow light colors, larger, longer Lagrangian coherent rate. So when we increase this Lagrangian coherent rate, we reduce the dispersion. So what we are saying that with longer Lagrangian coherent rates, we identify regions of less dispersion of material. But I mean, this is suspected because we are using backward trajectories of particles to define the Lagrangian coherent eddies. So, of course, it's going to be like that. But what's happening if we launch the particles instead of backwards in time, forward in time? We want to check if the Lagrangian vortices that we have identified back in time have some kind of predictability capacity. We have done the same, and we have this kind of, again, the same plot of the median absolute dispersion. It's pretty similar to the previous one, with the Eulerian vortices having the most, or identifying the most dispersive areas, and the Lagrangian coherent rates diminishing or minimizing the dispersion when increasing the Lagrangian coherent rate. So what information gives this? That even the Lagrangian coherent rates computed backwards, that trap the particles backwards, also have some, they're identifying regions where the dispersion of particles is minimized forward in time. When we compare what's happening backwards and forward in time, here you have it in dashed lines, the backward dispersion rate, and in solid, the forward dispersion rate. In the Eulerian case, there is not a preferred direction. However, in the Lagrangian vortices, there are a preferred direction backwards. It's evident because we are using these backward trajectories to compute them. But they are better than the Eulerian case. So, okay, that's it for the sensitivity study. So we managed to demonstrate that the Lagrangian coherent vortices trap more effectively the material than the Eulerian case. And we felt encouraged to do an atlas of these Lagrangian vortices across the 30 years of altimetry observations in the Mediterranean Sea. We call it ENCLAVEMED, ENsemble of coherent Lagrangian vortices in the Mediterranean Sea. And we have used a Lagrangian coherent rate of 40 days. Why 40 days? Well, another study from Ismail shows that starting with 40 days, we start having a high correlation between the Lagrangian vorticity and the Lagrangian eddy kinetic energy, meaning there are a close relation between the spatial variations of the Lagrangian vorticity and the Lagrangian mesoscale activity. So Here you can see all the Lagrangian vortices identified in the Mediterranean Sea, and the colors along the lifespan. All the days that we are tracking, that we are able to identify the structure in the same position or very close positions. And we can see very long structure up to like more than 1 year long structures in a very well-known areas. That we already know that there are some vortices with Eulerian approaches. But there are some regions where we have very scarce identification of vortices. It's mainly because of the algorithm. They are very narrow. But since the trajectories or the simulations launch the particles to the coast, so we cannot have a lot of structures identified. We have, as I show you, some spatial variability, but also we have some temporal variability. This is the number of vortices identified through time, and there are a lot of variability, but it seems that we have very well-defined seasonal climatology with more numbers of vortices identified in the summer rather than in winter. Also, as we have seen before in the sensitivity study, we have an asymmetry of polarity of anticyclonic versus cyclonic eddies with a more dominance of anticyclonic eddies. Also, we have found that it's a kind of a positive trend in the number of eddies that we have found in the Mediterranean Sea. So yeah, this is all sad. So of course, we have found, or both have found the same in the kinetic energy. There is a positive trend in kinetic energy in the Mediterranean Sea. But what I want to show you are the advantages of.
So it's all set and the ADP, no? So
Yes,
you add
yes.
also
Yeah, it's the ground one. Yes.
Grow.
Yeah, it's the geostrophic velocities.
Yeah, but the total, no,
Yes.
not on the anomalies.
Yes, yes. So what we're interested, or what I want to show you, are the advantages of this new Lagrangian vorticity atlas compared with previous Eulerian vortex atlas, in particular Meta 3.1. Here you can see just a snapshot of 1 day of what the atlas look. In orange, the Eulerian atlas, and in blue, the Lagrangian atlas, and you can clearly see there are much less identification of eddies in the Lagrangian product than the Eulerian one. You can see that this is the total number of Eulerian eddies identified across 30 years, and this is the number of Lagrangian ones. So we have done the same exercise as before, and we have tracked the particles launched initially in the interior of both the Lagrangian and Eulerian product. And we have computed the mean absolute dispersion, and we have divided each Lagrangian and Eulerian product into the ones that have matching, like collocated Eulerian and Lagrangian structures called matching, and then all of them to track if there are any differences. So you have computed the dispersion and the mean dispersion of these clusters of particles for the ENCLAVEMED, and then for the Eulerian one, the Meta 3.1. And we can see that the Eulerian, the clusters of particles initialized within the Eulerian vortices disperse more than in the Lagrangian case. However, the Eulerian vortices that match with the Lagrangian ones in yellow are less dispersive than when we consider in all the Eulerian vortices. What this means that, again, the Lagrangian vortices are identifying regions less dispersive than the Eulerian ones. We have compared with a test control that we have performed just putting some random circles and initializing the particles in random circles across the ocean and checking the dispersion. And we have seen that, yeah, both datasets, the Eulerian and the Lagrangian one, disperse or identify regions with less dispersion than the mean of the basin, but the Lagrangian ones are even less dispersive than the Eulerian ones. I've done the same for backward trajectories, and again, we have found that there are more dispersion for the Lagrangian vortices. However, when we check in the Eulerian case, the forward trajectories for the matching Lagrangian and Eulerian structures, they're very similar. And we consider all the structures, again, the Lagrangian vortices in the forward case identified more or less dispersive areas than the Eulerian case. Again, with the test control, we have found a much more dispersion. All of this has been done with the same velocity field based on altimetry data, but we wanted to test what's happening with real platforms, with real Lagrangian platforms, Argo floats. So we have computed the distance we have identified the Argo floats inside these structures, both Lagrangian and Eulerian vortices. And we have checked the distance between the center of this structure and the position of their Argo float through time. And we have normalized by the Lagrangian vortex radius. And we have obtained that for the ENCLAVEMED vortices, the Lagrangian vortices, the distance is smaller through time than for the Eulerian vortices, meaning it's suggesting that, again, the Lagrangian vortices track more effectively the structures, the Argo floats than the Eulerian ones. Here you can see with this probability distribution plot, how after 40 days of tracking the position of the Argo floats, we have found that more than 50% of the Argo floats initially found within a Lagrangian vortex remained within a distance of one Lagrangian vortex radius. In the same case, in the Eulerian case, we obtained only 30% of the Argo floats. Here you can see a very nice example from Leo and Abernathy in 2023 that shows how a Lagrangian vortex using the same algorithm as we do in the Pacific Ocean can trap very effectively an Argo float. In red you have the Lagrangian vortex, and in yellow the Argo float. So you can see how the vortex is evolving through time, and the Argo float it's maintained within its interior and tracked across the ocean. So yeah, that's it. We managed to the end. So just 3 take-home messages. So I wanted to show you the improvement of using Lagrangian approaches versus the Eulerian point of view to track the structures in the ocean, because the Lagrangian approach can manage to capture material coherency through time and space simultaneously. However, the Eulerian point of view, even if we can track the through time, we cannot assure that the material contained within an Eulerian vortex is kept in time without any spilling or dispersion. We have computed rotational coherent Lagrangian vortices in the Mediterranean Sea, and we have tested how the properties of this atlas or these vortices change when we change the Lagrangian coherent rate, the time that we use to track the particles to compute the Lagrangian metrics. I've seen that increasing this Lagrangian coherent rate reduces the dispersion of the particles within its interior, in both when we launch them backwards and forward in time, but also increase the asymmetry with a dominance of the anticyclonic vortices identified. Also, we have developed a 30-year atlas of Lagrangian coherent vortices in the Mediterranean Sea that again are less dispersive, identify regions less dispersive than the Eulerian vortex atlas, and can trap Argo floats real platforms more effectively than the Eulerian vortices. This work, from these works, we are going to prepare, or we are preparing two papers that hopefully will be submitted in the upcoming months. So yeah, that's it. Thank you very much. I will leave you with this.
Thank you very much, Diego. Any questions?
I had a couple of questions. Yeah. Well, thanks for the talk. It was very interesting. So I'm not I don't do fluid dynamics in this case. So probably the question is completely crazy, but I had a couple of questions about the transport. So
yeah.
when if I think about parallels, when you look at transport, for example, in smaller scales in networks of rotating cells, right? You have to be very careful, obviously, of what happens when you have objects that are close to very tightly packed streamlines. Because small changes there can obviously make you go amongst choose different paths that diverge very quickly, right? So the type of transport that I was wondering, the type of transport that you can predict from the data that you have, how should one think about it in terms of the fact that most likely you don't really have a lot of fine scale data on what happens really at that scale when you have objects that are close to diverging streamlines. That was one. And the other one, meaning, do we have to think of it in just in a statistical sense, or we have to think of it in a different way? And the other thing was related to regions of upwelling and downwelling currents, because obviously you can only see what happens in the surface. So I guess that, for example, again, it's a guess, that in different periods of the year, you're going to have stronger upwelling and downwelling currents. I don't know, maybe in the summer you have less, and in the winter more. And the actual transport of stuff that is not afloat will depend on that as well. So how should we think about or try to incorporate that?
Okay, so yeah, related with the first question, we only, I mean, from conventional altimetry satellites, we only can get the geostrophic flow. So all the small scale processes and structure, we cannot see them. I mean, they're of course happening, and we see in the for example in the drifters, we can see that there is not a perfect match between the Lyapunov exponents and where the drifter goes. So there are some small scale dynamics happening there that we cannot see with the model. Sorry, with the observations, but we just wanted to focus here on more on the algorithm regarding how we identify these structures. Of course, the process is resolved we have a limitation of the process that we can resolve with this spatial resolution. But with these types of data, we cannot access to them. Maybe with SWOT, yes, but we have a very short. It can be a good exercise to check what is happening with this new satellite that allows us to track or to access or capture very small processes. But here we are focusing on the point of view rather than having the data that we have. How can we improve the identification of this structure, or even so saying that maybe the way that we are seeing the vortices and how they trap material, it's not the correct one, or we can improve that even if we know that all the processes are not very well resolved, or the small scale processes are not well resolved with our data. And even we have in our algorithm, we have a lot of different parameters that we can tune to kind of try to be more permissive with the dispersion, taking into account some other processes that maybe are not accessible with the data set. And the second question, yeah, this is just for the surface. And usually all these works are done in the surface, but we can do the same exercise, this transport across the different layers in the ocean, and we are going to have a different result. But it's going, I mean, this is already a very time-consuming computation. We are launching millions of particles across time. So it takes a lot of time. For example, the ENCLAVEMED products that took 2 months to compute. So adding more three-dimensional model also, like, we have to have confidence in the vertical velocities. That I don't know if we can. So yeah, I mean, it can be done, and it would be a very nice exercise, but it's a bit difficult to rely on the results even because of these vertical velocities, for example.
I was curious about the eddy in Ibiza that you mentioned. So this comes from the Millennium topography, probably, no? Or, so
Yes, in
so it's almost
2022.
permanent.
Yeah, it's like for almost like 100 to 120 days. I found that a cluster of particles that are that remained together in this area. So
So 120 days over the whole 30 years.
no, this is just 1 year. This is only 2022. Yes.
Okay, so that was that particular.
Yeah, it's a particular date. Yes. But we find in here we find a lot of different structure that are around like 90 or 100 days long, also in the surroundings of the Balearic Islands. So it's very during the 30-year period.
I'm so curious also about this one south of Greece, because we know that the one in Petra that
Yeah.
is not east of Crete, but this one, the other one, south of Greece.
This one,
This one?
yes, but in Eulerian in the Eulerian perspective, they also like Peliasco in 2021, they identified this structure also.
And what's the name? Because usually these have names.
Yes, I don't know. It's like
Yeah, Petra, Mersamanti.
I don't know, I'll see you later. Yeah, it's called,
Maybe appeared after I studied.
yeah,
It's-
and in several papers, they have this structure identified. Yes. It's called something Peloponnesian eddy or something like that.
ah,
Yeah.
Another question? So we can leave it here. Thank you very much.
Thank you.